Well, it's really nice to be here in Wales. I gave a departmental colloquium, and I mentioned this. Half my family is actually Welsh. They're from near Cardigan. The name is Edwards. Apparently, everyone in Cardigan's named Edwards. So when I showed up there a few years ago and said, "Hey, I'm here," I didn't necessarily find my direct relatives. So I found a lot of people named Edwards. But it's not. It's been great being here. I've been here 3 weeks, and my stay unfortunately comes to an end on Saturday. I got to go back to work at Berkeley. There's clearly been a lot of interest in what is loosely called 3D movies, television, video games, etc. You've all heard about it. You've seen it on TV. You've seen it in the newspapers. And so that's what I'm going to talk about today. And so let's start by saying what's the big deal? I mean, why is there all this excitement? Well, part of it has to do with money. Avatar set a record for box office receipts, and it's still going because it's still being shown. It's currently, the last I looked, at $2.8 billion of box office. Alice in Wonderland was $1 billion. Toy Story 3 was 1.1, and they were all of them made most of their revenue in stereo 3D. They, of course, came out in conventional 2D as well, but most of the revenue is from 3D. So that generated a lot of excitement in the entertainment industry. Likewise, in television in the States, ESPN is trying to get together a sports channel that would have steady stereo 3D. It hasn't really happened yet. It's just little tidbits here and there. B-Sky B is doing the same for pubs and football matches. Video games, you probably all know that Nintendo came out with a 3D game called the 3DS, and PlayStation 3 from Sony has a stereo 3D version. There are also, aside from entertainment, there's some really exciting developments in various areas. I'm just going to hit a couple here. One is in medicine. This is a surgical system, which is really a robot-assisted device. So the user, you can see his hands here. The surgeon has his hands in a device that controls these tools, and typically is currently used where the surgeon's right next to the patient. It's not done over the internet or something like that. But tremendous advantages. The tools are much smaller than the hand. If the surgeon has a little tremor, you can filter that out with the robot. There are manipulanda that they can do with the tools. You can't easily do with your hand. And the question is, how does the surgeon see what's going on? And they're looking through this device, which is a stereo 3D device, at the tools in the patient. And they can magnify the view so that rather small movements actually look pretty big, so to improve the accuracy of the movement, et cetera. Great stuff, because it makes the incisions smaller, the recovery time is better. Surgeons can probably work now until they're 80 because the tremor won't matter so much, et cetera. CAD/CAM, we're actually working with a company that does computer-assisted design, computer-aided machinery software in 3D, and that too has been very useful. Science, mapping the brain and seeing what different forms of it look like. It's easier to do when you get a clear 3D percept. That's not going to show up very well below. That's from geology. It's if you could fuse the two images together, you can see where the earthquake centers were off Australia and New Zealand in depth. And geologists can tell what kind of tectonic plate activities cause earthquakes by seeing the 3D structure of where the earthquakes occur. And that's really hard to do from the visualization you normally see, which is just kind of like a bird's eye view of where the events were on the surface. Very useful. Okay, so let me tell you a little bit about how it works. I know many of you know this, but some of you probably don't. So let's just talk about that briefly. Here we have two eyes that are looking at this green object. And an image is formed of the green object in the back of the two eyes. And I just want you to notice it is formed in different places in the two eyes. If you will, this eye sees the scene something like this. It's looking at the green object, and it sees the right object to the right of it. And the other eye sees the opposite. It's looking at the green object, but it sees the red object to the left of it. And the difference in these images we call disparity, binocular disparity. And it's that difference between the two eyes' images that creates the impression of depth. So in other words, we can go from an image like this in the left eye and an image like that in the right eye. If that's all I presented to you, you would see something in depth like this. And that's that creation of that compelling sensation of three-dimensionality from disparity. That's what's going on. That's what the big deal is all about. Here's an image that conveniently of San Francisco's Golden Gate Bridge that shows an application of that technique. Now, I want you to imagine that you're looking at the green image with your right eye and the red image with your left eye. And you can see here, that bridge tower, there's quite a bit of disparity, difference in the two images because it's pretty far away. If we follow the banister closer, we can finally see the two images come together about here. And so that changing difference in the two eyes' images is what gives you the impression of depth. That's a very compelling picture in depth when you have the red-green glasses. Well, people hate wearing red-green glasses and watching film and TV, so one of the reasons that there's so much excitement currently is new technologies that allow you to see the two images differently without that color difference of the two eyes. And I'm just going to show you two, because you're going to be seeing them more and more. One's called liquid crystal shutter glasses. This is likely to be the technique that's used for television. So if you actually probably own a 3D TV set and you don't know it. If you bought one recently, it's 3D capable. There's just a switch in there they're going to turn on for you sometime in the future, and then there it goes. And the technique it's very likely to use is this. These shutter glasses are electronic, so they can open one eye to make it transparent while the other eye is opaque, and then do the reverse. If you go from left to right, you can see over time we go from right eye transparent, left eye transparent, right eye transparent, left eye transparent. And here's what a typical set of glasses look like. They have a little power source and receiver of infrared light that synchronizes to the TV set. So what the TV does, this isn't a TV, this is a projector system, but what your TV is going to do is present the left eye's image at one moment in time, so the glasses will open that eye's image, and then it'll close, open the other eye, and then it'll show the right eye's image. And it goes back and forth 120 times a second, so it looks pretty solid and non-flickering. That's the liquid crystal shutter technique. Common in television, uncommon in the theater. In cinema, kind of the winning technology at the moment is from a company called Real D, and here's how it works. They have a projector that projects to the cinema screen, and in front of the projector they have what we call a polarization switch. So the light polarization, you all know that light can be polarized, so the waves are going this way or they're going that way. That's what we call polarization. You can actually polarize it circular as well, so the light's actually going like this. That's, from your perspective, that's clockwise. Or it could be going like this. That's anti-clockwise. And that's what this procedure does. So with that polarization switch, at one moment in time, they make the polarization clockwise. And then you're wearing glasses, these passive lenses, and the left eye transmits clockwise polarization, but not anti-clockwise. So you see the image that's meant to go to the left eye at that moment in time. Then they switch the polarization switch to do the other rotation, and then you see that image with the other eye. And again, they're flipping back and forth between these two quickly enough that hopefully you don't see it flickering. That's how it works. Okay, but you've all heard about the health concerns. And this is, I think, a pretty reasonable warning from Sony in their user device notice with PlayStation 3. And you can read it. It says, we recommend that all viewers take regular breaks. Seems sensible. Length and frequency of necessary breaks may vary from person to person. Some people may experience discomfort, such as eye strain, eye fatigue, or even nausea while watching 3D video images. Okay, so just warning people that there have been reports of discomfort, headache, blurry vision, etc. And so it seems like a fairly appropriate product warning. Here's another one. I'm sorry it's so small, but it's a long warning from Samsung. And if you can't read it, I'm just going to read some of these sections here. Some viewers may experience an epileptic seizure or stroke when exposed to certain flashing images. Well, that's true for conventional TV too, I guess. So if you have a family history of epilepsy or stroke, please consult with a medical specialist before using the 3D function of your television. Pregnant women, the elderly, sufferers of serious medical conditions, those who are sleep deprived or under the influence of alcohol, that leaves me out at night, should avoid utilizing the unit's 3D functionality. Goodness. Whoops. You may experience the following symptoms: altered vision, okay, reasonable, lightheadedness, maybe, dizziness, involuntary movements such as eye or muscle twitching, confusion, nausea, loss of awareness, convulsions, cramps, etc. So this is pretty unreasonable, and obviously sparks a lot of concern from the public and from the press when you read product warnings like this. The British have a great newspaper called The Sun, and this is a headline that appeared back on May 3rd. Nintendo 3DS is a game for a barf. Great. So there have been clearly some health concerns, and I get calls all the time from the press and from various people just asking are these concerns valid or not? And what I'm going to tell you about today is kind of what we know and what we don't know, and hopefully you can come away with some feeling for what's reasonable and what's not, and most importantly for what we don't know and should know in the future. So I think there are a variety of, I'm going to call them user issues. Some of these are not really health concerns, but some of them could conceivably be. I'm just going to call them sort of annoyance factors and discomfort factors at least. I don't know if they're real health concerns or not. And the one I'm going to talk about two today: visual discomfort due to divergence accommodation conflict. We'll come back to that. So let me just tell you a little bit about the ones I'm not going to talk about. Conflict between visually induced motion and vestibular signals. How many of you saw Avatar in 3D? Okay, the flying sequence where you're flying through the canyon. Most of us got a compelling sensation of really moving through space because the visual input was consistent with that. But of course your inner ear is saying you're not moving. And for some people that conflict between the visual sensation of moving and the inner ear vestibular sense of not moving can cause motion sickness or nausea. And there have been clear reports of people experiencing that in that sequence in Avatar and in other films. Now, why are we concerned about that with stereo? Because stereo adds to the compellingness of the visual sensation of motion. So it's not a trivial concern. It actually is something I think we ought to pay attention to and see how many people experience it. Head roll and discomfort due to vertical divergence eye movements. Again, television. You know, if I'm watching TV, the last thing in the world I'm doing is sitting bolt upright in a chair. I'm laying inside half asleep and right, so my head's tilted like this. That's a problem with stereo TV because the images are displaced horizontally. If your eyes are displaced like this because you have your head rotated, then to combine the two images in your brain, you have to make a vertical disconjugate movement and horizontal. And these vertical movements, when one eye goes up and one eye goes down, it's called a vertical divergence eye movement. They're uncomfortable. And if you have to make a big one and sustain it, you can feel pretty tired and uncomfortable. So I think that's a concern. Head orientation is going to matter. I will talk about perceptual distortion, so we'll come back to that. Flicker and motion judder, it's interesting in this stereo technique, because they're opening and closing the two eyes images like this, when one eye is illuminated, the other eye is receiving nothing. Okay, so if you think about what the eye is receiving, it's bright, dark, bright, dark, bright, dark, right? Same for the other eye. That increases the sensation of flicker, that the thing is pulsing like this, because that's really what's going on within an eye. And it also increases the sensation that the motion's not smooth. I'm sure you all saw this in some of the scenes in Toy Story 3, for example, when they panned the camera like this. The figures kind of look like this, and then they settle down once the camera pan stops. To a large degree, that's due to this on-off thing they have to do to get the images separate to the two eyes. So we call that motion judder, that second thing. Window violations are something that happened at the edge of the screen where the content, that one's kind of hard to explain, so it's just where the content is not at the right place relative to the edge of the screen. Ghosting is where one eye is seeing the other eye's image a little bit. So if your glasses aren't really high quality glasses, or you don't have them on quite right, the left eye might see some of the right eye's image, and that looks like a ghost and can be at least annoying. Okay, so let's talk about visual discomfort due to divergence, accommodation, conflict. In the real world, we're typically looking at an object like here, and there can be other objects over here that we're not looking at, and it's closer. So to look at this red object, we have to direct the eyes, both eyes to it. If we didn't, right, if I cross my eyes, I see double images. So to see one image, I've got to direct my eyes to it. And that the eye movement we make to do that we call vergence. So that's this eye movement where your eyes are going in and out. We also have to focus the eyes so we see a sharp image. And we do that by adjusting the shape of the lens inside our eye up until you're about age 45. After that, you don't do it anymore. As someone says, you learn to focus after 45 with your neck muscles instead of your eye muscles. But young people, they focus to different distances by adjusting the power of that lens. Now, normally you're looking at, meaning converging on, and focusing on, meaning adjusting the power of that lens, to the same object. And so vergence and this focusing response, which we call accommodation, are at the same distance. Here's another object over here that is at a different distance. And so if I took this might be what the image looks like to me. The thing I'm looking at is sharp, and the thing I'm not looking at is blurry because it's much closer. So that's the way the real world behaves. On a conventional computer display, that's not true, because on a stereo display, because now we simulate an object being here, let's say at the distance of the display screen, and that other object that we're simulating to be closer, we can do it with that cue of disparity I told you about, but the light's still coming from the screen. And so we can't get the right blur because the light's all coming from the same distance. And so this accommodation cue now is off. What you want to do is accommodate to the screen, not to where you see the image in depth. And we call that the vergence accommodation conflict. I'm going to show that to you in a different way. Here we've got two eyes looking at a point, so they're converged in that point. That's the vergence distance, the distance to which the eyes are converged. And they're also focused on that distance, that's the focal distance or the accommodation distance. And we like to plot this in these funny units that optometrists have given to us called diopters. And here we go. Diopters are the distance inverted. So if the distance is 2 meters, we invert that. 2 over 1 is 1 over 2, so it's a half diopter. A half a meter, we invert 1 over 2 and we get 2. So a half a meter is 2 diopters. And that's what's plotted on these axes here. So 0 corresponds to infinite distance, and 5 diopters to 1/5 of a meter, or 20 centimeters. And then this axis is plotted the same way. This is infinitely far away, and this is very close. So this is the accommodative distance and the divergence distance. And as I said, the real world basically lies on this line where those two distances are the same. We know from the optometric literature that there's a zone. I've just drawn this as a cartoon. This isn't technically correct the way I've drawn this. But there's a zone around this 1-to-1 line where if you saw a stimulus like that, you actually could focus it and make it into a single image. So you could manage the conflict. You could arrange it so that you focus a little bit closer than you're converging your eyes, for example. And we call that the zone of clear, meaning sharp, single, meaning not double, binocular vision. The zone of clear, single, binocular vision. So in other words, the visual system has some tolerance for a difference in divergence and accommodation distance that it can handle. Within that zone, there's a smaller zone called Percival's zone. There's another one related to it called sheared zone that's very similar. And the notion here is these are the conflicts that you can manage and remain comfortable. So the light orange zone is a region where you can manage the conflict. You can make it single and clear, but it's going to be uncomfortable. The dark orange zone, the notion is that it's a comfortable conflict. Now with a stereo display, like your stereo TV or stereo cinema, the display is at some distance from you. The stereo content can create the impression of an object, let's say, behind the screen here. So that's the divergence distance. That's where your eyes would have to converge to make that object single. But the light comes from the display screen, so to focus it, we have to focus at that distance. And in our plot here, that looks like this, where the display screen is some distance, and as the producer of the film moves the content from behind to in front, it moves left and right like this and in and out of that comfort zone. So that's what gave rise to this notion that this conflict could make people uncomfortable, is the content of the image you're looking at on the film or in TV could well fall outside this comfort zone. So we wanted to study this. Just because it occurs in optometric patients does not mean it's going to occur in the cinema or watching television, because putting a pair of glasses on and wearing them a lot, like most hours of the day, is very different from watching a half hour of sports on television. So our concern is that this may be a valid concept for optometry, but it may not be a valid concept for watching stereo content in cinemas and televisions. So we built these displays that allowed us to do research on this. We're pretty proud of this one display, so I'm sorry I'm probably going to spend more time on it than you're interested in me spending, but we're proud of it. This is Gordon Love at Durham University in the Department of Physics, not too far away from here. And this is the display we built. The light comes in this way, and the viewer's eye is here. And we have these special lenses, which I'll show you in a minute, that can change power very quickly. And one of the lenses looks like, that's actually the full set of lenses right there. And what we do is we put the lens between the viewer's eye and the television, and we can simulate objects being far away or very near by changing the power of this lens. And that gets rid of the divergence accommodation conflict. Here's how the lens works if anyone's interested. Here's a picture through our system. So we put the lens in the near state and then just put up a camera and took a picture of some real objects. And you can see that with our lens, we can make the near one object in focus, or down the lower right, all we did is just electronically switch our lens to another power, and now the far object's in focus. And we never changed the camera. The camera just sitting there just shooting pictures as we go through the sequence. Okay, I want to show you how this thing works. So I'm going to play a, whoop, missed it.
The following videos are time-lapse recordings of images viewed with the switchable lens display. In the first segment, the switchable lens is turned off, and we slowly change the camera's focus from near to far. At the far distance, the camera is focused at a distance farther than the display. Notice that the whole image comes in and out of focus together. This time, we activate the switchable lens and again focus the camera from near to far. Now each part of the image comes into focus separately when the camera is focused to its simulated distance. Depth-weighted blending in our software produces a continuous change in blur on the ground plane. Now the switchable lens is turned off and the camera's focus is fixed. An object moves slowly from near to far and then from far to near. The camera is focused at the distance of the display screen, so the moving object remains in focus throughout. This time, we activate the switchable lens and hold the camera's focus fixed again. The object is in focus when it's near, but becomes blurred as it moves farther from the camera. Then it becomes sharp again as it returns to a near distance. These videos show how our display, based on a high-speed switchable lens synchronized to the computer display, can create realistic images in which focus cues are correct.
And the trick is to do this very fast. So we do it at 180 hertz, 180 times a second, so that you can't see it changing. So it just looks like a fused volume. Okay, if you didn't understand that, fine, but I just wanted you to know it's cool. And what it allows us to do is now under computer control, we can now manipulate this divergence accommodation conflict, which you can't do on a conventional display. Now we've got control over it, so we can study the consequences of it. Oh, yeah. When I was in Durham, part of my sabbatical, the press called up and said, we hear you're working on this new display and we want to come. And so we did this fairly serious interview where we thought this guy was really trying to understand things. And this is the article that came out in The Sun. You ready? Brit 3D is bar-free, a new 3D system that mimics natural eye movements, not really, has no side effects, claim its Brit creators. I became a Brit. Unlike conventional 3D, which flashes different images at each eye, the new glasses-free screen, also not true, it has glasses, shows images with different focus depending on where users look. Sort of true. The Durham University team hope InFocus 3D, that's the name we adopted, will be used by TV and game console makers. We actually have a practical way of doing this. The display you saw is not practical. No one's going to want to have that in their home. But we have a more practical and simple way to achieve a lot of the things this thing can achieve. Okay, so the question is, do divergence accommodation conflicts actually cause discomfort and fatigue? It had been said repeatedly that it does, because there's been a long history of people looking at these stereo 3D displays for like a half an hour and then coming out afterwards and saying, man, my eyes are really sore. And so it was believed that something is causing problems for people. Okay, that's fine, but you don't know what. It could be the glasses they're wearing, it could be ghosting, it could be the content, maybe you don't like the content. It doesn't say it's the divergence accommodation conflict. The only way scientifically you can prove that that's what it is to make everything else the same and either have the conflict present or not. Otherwise, it's just not logical to conclude that you've shown that this one factor is causing discomfort. And unfortunately, that's what the state of the field is. The typical experiment was done. You show somebody a stereo movie. At the end of a half an hour, you say, how do you feel? My eyes are sore. I have a headache. Aha, the divergence accommodation conflict caused that. That's just not logical, I'm sorry. So what we did is use this equipment to really look at it. We created two kinds of conditions. The first we call cues consistent. So what we did is we created a stimulus at some distance where you had to converge your eyes and focus your eyes, and then we'd jump it to a new distance, like here, at some time later. So you had to go from looking here to looking here, like you do in the real world. We call that the cues consistent condition. The cues inconsistent condition behaved like a stereo 3D display, like your TV set behaves, if it's 3D. We would start with someone looking at some distance, focus there and converge there, and then the content would do this funny thing that happens on your stereo TV, which is the stereo content might come forward, so you had to converge your eyes. Got to get the pointer back there. While you had to focus your eyes here, because of course the light's still coming from the screen. Okay, so we're mimicking a stereo display where the screen is here, but the content is jumping around. So that's what you're doing when you watch a movie. We call that cues inconsistent. And we had people do a task. They had to find a stereoscopic figure as this thing's jumping around, and we led them to believe that they were being paid for how well they did in this task. It turns out that wasn't really the truth. They were just getting paid for participating. But that motivated them to really try hard, to really look at each trial and do the best they could. And then at the end of, we didn't know how long it would take to cause these people fatigue, so we actually subjected them to 45 minutes of this. And they were randomly in the cues consistent or the cues inconsistent condition. Every person was in both in random order. We didn't know which condition they were in on a given day, and they didn't know, so it's what we call a double-blind experiment. And at the end of each session, we basically asked them, how do you feel? So here are the 5 questions. How tired are your eyes? How clear is your vision? How tired or sore are your neck and back? How do your eyes feel? How does your head feel? And then on a 9-point scale, they had to tell us about the severity of their symptoms. 9 being really bad, and 1 being no problem at all. The orange is the cues consistent, and the blue is the cues inconsistent. And you can see for questions 1, 2, 4, and 5, we got a significant difference where people judged the cues inconsistent to be worse in terms of symptoms. There was no difference on the neck and back. Well, we didn't expect there to be a difference. We threw that question in to make sure that people are really answering the questions, right? The neck and back was a problem no matter what you're in, because you're in this equipment on this thing holding your teeth still. And so that's good. And these are all significant differences. So that really shows then that it is the vergence accommodation conflict, that it is a source of discomfort. Doesn't mean it's the only source, but it's a source. We asked people also to compare the 2 sessions. So remember, everyone went through 2 at least. Sometimes they went through 4. And at the end of every pair, we said, tell us about what they were like relative to each other. Which was more fatiguing? Which one irritated your eyes more? Which gave you more headache? Which one did you prefer? And anything above the dashed line means they liked the cues inconsistent one less. So that again shows that this vergence accommodation conflict is deemed to be less comfortable than when the conflict's not present, even though everything else is the same. More recently, I'm going to kind of go through this quickly. Very quickly. We did more studies, and so I'm going to just show you the result. So we've looked at this more to try to measure the effect of distance, whether it matters if the content is behind the screen or in front of the screen, etc. And we can summarize the results with this slide here. This is a summary of the new data, where here's the vergence distance, and here is the distance of the viewer from the screen. So that's the accommodative distance. Again, these units are diopters, so I know they're kind of funny to understand because they're inverse distances. And I put in this slide the distances of typical things. Like cinema, people sit pretty far away, so that's near 0 diopters. Television, again, fairly far, near 0 diopters. Desktop display, around 2 diopters. People tend to have those at about arm's length. Mobile phones are yet closer, about here. And the blue and red lines are our best estimate of the boundaries of the comfortable zone. If you get out beyond those lines, if you get out here with your mobile phone, that's likely to cause discomfort for the average young viewer. All the viewers, I should have said, were 20 to 32 years of age. Television and cinema, it's a different range. It looks kind of restricted here. This is an important graph that shows really what producers of content are going to want to know. Here we have the divergence distance now in meters, so I've undone the diopters. So these are units you're more used to now, so that's far away, that's near. And this is the distance to the screen, again in meters. So cinema, the average distance for viewers is around 20 meters, television around 3 meters, desktop display around 50 centimeters, mobile phones around 30 centimeters. And there are our blue and red boundaries of the comfort zone again. And this slide makes the important point that the farther away you go, the more distant you are from the device, the bigger the range of comfortable viewing. So that's why I think cinema might be here to stay. It has a real good chance of, when done right, leading to comfortable viewing. Mobile phones, I'm worried about it. And you can see why, because you're getting down into this region at that distance where the range of comfortable viewing is restricted. So you have to really worry about the content on your mobile phone. Desktop displays, not quite as bad, but also needs some thought. I could tell you more about this, but I want to move on. We hope that the producers of content are going to use data like this as we refine it further to help design their displays and give really scientific-based recommendations on viewing distance and what kind of content should be looked at and for how long and things like that. The things we don't know just boggle the mind. We don't know the effect of the age of the viewer, really. We don't know if it matters if you're nearsighted or farsighted. We don't know if it matters if you have lots of experience with these devices as opposed to little experience. There's a lot of things we don't know. And I guess we're going to find out. Okay, last topic. Perceptual distortions due to incorrect viewing position. We had been studying the ability of people to look at a conventional picture, just a photograph, at odd angles and determine what the content of the picture is. And I think I'm going to go kind of quickly through this and just give you an idea of what we did. We had people look at pictures like this, and they had to judge the shape of this central object here. And the trick was, on the computer display, we'd rotate it like this. So you had to look at it at a known oblique angle, the wrong angle, right? You should be looking at it head on. And then we had people judge the shape. And to make a long story short, what people do is shown here. The blue data points show what happens when a viewer looks at one of these things with 2 eyes and can see the whole picture. So if they're looking at it like this, what it tells us is what they perceive. And the fact that the data lie on one or very close to it mean that people can compensate for being at the wrong angle. They see basically the right shape. So the brain has the ability, when you look at a photograph, you can rotate it and see basically the correct shapes. So it doesn't matter so much that you're at exactly the right place to view the photograph. There's only one correct place to view a photograph from, but you don't have to be there. I said this at the department colloquium, but a lot of you weren't there. If the reverse was true, if it really mattered where you sat to what you see, then you all would have arrived a half an hour early if you cared about what I'm going to say, and you would have rushed to the one seat, which would have been right there. That would have been appropriate, and everyone else at the sides would have been pretty unhappy with their perception of the slides. That doesn't happen. The brain has an ability to compensate for your off-axis viewing position with conventional pictures. And thank heavens, that's why we can have theaters, and that's why we can have rooms laid out like this, and no one really cares that much where they sit. But we had reason to believe that's not true for stereo, and what I'm going to show you is that we're right. It's different for stereo. So what we have here is just an old 2D photograph, and the two eyes, if you looked at it, if I had it in front of you, you'd look at it with your two eyes. And we know that using your two eyes helps you compensate for the angle of view, that's important, looking with two eyes. But a stereo picture, this would be one where you might look into it with a stereoscope, so the left eye sees this image and the right eye sees that image. Now the two eyes get different images. They're constructed that way. And that makes it difficult to imagine how the brain could compensate for being at an odd angle. The reason why is the disparities are all changing in the image, and some of them are caused by the picture being slanted, and some of them are caused by the content of the picture. It's confounded. How's the brain supposed to know which part of those disparities of my eyes are due to the fact I'm looking at this odd angle versus which part of it is due to what the scene is? So that's why we suspected that people would compensate less well for being in the wrong position when they looked at stereo photographs. And so we did an experiment. And this kind of shows how it works. We had a display, and we had a projector that projected the image that's going to go to the right eye, and a projector that projected the image that's going to go to the left eye. And we made an image of what we call a hinge. So it's something that looks like this. And it might be rotated like that, or it might be rotated like that. And your job was to say whether this angle was less or more than 90 degrees. So if you look at that, you'd say less than 90 degrees. Okay, I'll open it up. Less than 90 degrees. More than 90 degrees. So the computer would move it back and forth until it was actually, to you, it looked like 90 degrees. And then we looked at what you did to figure out if you were able to compensate for being in a weird position. And so, of course, we put the viewer over in this odd position. The right eye is seeing the red image, and the left eye is seeing the green image. And if the brain fails to compensate for this unusual viewing position off to the side, this hinge that we're trying to portray is going to look like this hinge, this orange thing. So when you move to the side, a hinge that actually is like that is going to open up perceptually. That's what we expected, okay? And it depends on where you are and which way the hinge is tilted and stuff like that. I'll show you in a minute. And here's what we predicted. This is the viewing angle. So here you are straight ahead of the screen, and here at 25 degrees to the side, and here you're 45 degrees to the side, quite a bit to the side. And this is how we predict that a person would set the hinge to make it look like 90 degrees. So if they always did it correctly, they'd set it to 90 degrees, and it would be 90 degrees. So that would be if you were able to compensate completely and accurately no matter what your viewing position was. On the other hand, and these different curves are for different, the hinge might be like this, it might be like that, it might be like that. Those different curves correspond to which way the hinge was facing. And here's what we predict if the brain completely fails to compensate for your oblique viewpoint. If the hinge is oriented one way, you're going to make this kind of error. If it's oriented another way, you're going to make this kind of error, etc. You don't need to understand where those curves came from. It just predicts errors. We did this with non-stereo pictures, and here are the data. People are pretty good. Their settings are all close to 90 degrees. That's what I told you before, that people can compensate with a flat picture for their oblique or off-axis viewpoint. We already kind of knew that. So here again are the predictions for the stereo pictures. We predict big errors if you're not compensating for your strange position. And there are the data, color-coded relative to those predictions. So you can see that that's pretty much what people do. Now, next time you go to a stereo film or you see a stereo photograph, look for our effect. Hold the stereo photograph if it's a picture, or if you're at cinema, walk left and right, and look at some structured thing like a corner of a building or something that you kind of know the shape of. And when you walk like this, you'll see that the angles can open and close depending on where you are. And they tend to rotate towards you. And that the side nearest you tends to lengthen perceptually, and the side farthest from you tends to shorten. Those are all effects that you can predict by just thinking about how these disparities change when you're at the wrong place. Does it matter? I don't know, right? Maybe it does. If you have a picture of some random tree, I don't know what the shape of that tree is, so it doesn't matter if I'm seeing it distorted. If you had a picture of my wife, I know exactly what she looks like, and I'd be unhappy if her nose suddenly started doing this, because that's not what she looks like. So it'll be interesting to see how that plays out. Let's say it does matter. This is my cartoon of what could happen. So in conventional cinema, right, people are happy to sit anywhere and watch the film, and we, at least in the States, everyone pays the same for every seat. I don't think that's true here, right? Don't you pay different amounts for different seats in some theaters? But we don't. You pay the same for every seat. But with stereo, if what we're saying is correct and people are bothered by it, then there's going to be one seat in the house that's really good, and my argument is we charge that person 30 pounds for that seat because that's a privileged seat. And then over here, not too bad, so the price falls off. That's 7 pounds. Over here, that's a terrible seat, and so we'll let that person in for £1. This poor person over here, we're actually going to give them money to come because they might buy Coca-Cola and popcorn, so we'll make some money on them anyway. So this is actually a serious concern. I worry that we're going to have to rethink how we distribute audience seats because what we've learned from conventional cinema, conventional television, doesn't directly apply to stereo. So we might have to rethink that. Okay, these are the things I talked about among that long list. Visual discomfort due to divergence accommodation conflicts and perceptual distortions due to incorrect viewing position. And made the argument that divergence accommodation conflict really does cause discomfort and fatigue. As we begin to understand it, I think we can manage that by paying attention to viewing distance and the content that's shown, although we have a lot more to learn about that. And perceptual distortions due to incorrect viewing position, we're going to see how that goes. Most people don't seem to be that bothered by it, frankly. When I've talked to people who go to cinema and they sit at some strange seat like you guys are sitting at, and you ask them, well, what does that image look like to you? And they say, well, it looks great. So maybe people don't really notice it, and it's just we perceptual scientists who can measure it. But these other things have to be studied too, and work is proceeding, but maybe more slowly than we would wish. So the final thing I'd like to say, because it's a public lecture, is I hope this work is just an example of how, as Simon is saying, how societal concerns really can be addressed by things that people do at universities. I'm a psychologist by training. I work in a vision science department, but the training I have in psychology, it allows me to do this kind of work. So it really is the case that we can address societal concerns and make reasonable recommendations. And I also have to say that I've been very pleased that as we've been doing this sort of stuff, that the industry's been calling and asking us to come down and give talks. And you might think that they're just just trying to make bucks, right? All they're worried about is being sued. And it's not true. They really are listening, paying attention. They want to get it right to the best of their ability, the ones I've met anyway. And so that's been pleasing, that the industry seems to actually be paying attention to what vision science has to tell them. One of the great things about being in academia is you get to work with really good people. And here are some of the people who worked on that project. Gordon Love is a physicist in Durham. And the lens idea to make that display was primarily his idea. David Hoffman was a graduate student at Berkeley who programmed the display and did a lot of the experiments. He's now at a company called MediaTek. Takeshi Shibata was a postdoc at UC Berkeley who just went back to Japan, where he has a position at Waseda University. This guy was there at the beginning, and yeah, you may or may not know, has built a display that has some very interesting properties that is kind of like ours, but it's emphasizing different things. Kurt Akeley was there at the beginning and wrote some really important software that makes these multifocal displays possible. Juan Kim is a postdoc at Berkeley and worked with Takeshi and David and me on these fatigue studies, the more recent ones. And I left out a person, unfortunately. I realized as I look at this, Anna Gierschik was involved at the beginning in the perceptual distortion studies and in the fatigue studies. And she's gone to NYU, New York University, and has now returned to Berkeley nicely. So thank you very much for your attention.